Oh, well, this is for notes for Friday. It's Friday exactly. It's going to be day 45 of the trimester. Today we're going to be talking about Steel Standard 2.1. We're going to the previous day we had talked about work and power. Today we're going to actually get into kinetic and potential energy. So you're going to understand that a whole lot better when today's over with. As you said, they aren't making anymore, and we'll get into more later on about why they aren't making anymore. We'll talk about that in class today. All right, energy. Energy is the ability to do work. If you're doing work, you're using energy. So you have to get energy to be able to do work, and if you're doing work, you're using that energy. And using isn't maybe the best words to use because we associate using with using it up, and it's really just kind of transferring. Let's get into this more. Kinetic energy. Kinetic energy is when energy is moving. We have something that's moving. As the equation says, it's a mass, and when that mass has velocity, that's kinetic energy. Potential energy is stored energy. It has the potential to do something. And there's a couple different types of potential energy. There's chemical potential energy, but we won't necessarily get into that very much whatsoever at all. That would be like energy in gasoline or food, or it's the chemical breakup. What we're going to talk about here is gravitational and elastic. Gravitational deals with the mass, the gravity, and the height, because we've got some object, that's the mass, gravity's pulling down on it, and it has some height. It has stored energy. And then there's elastic. K, as we know from Newton's or Cook's law, K is this thing that deals with elastic objects, things that have lots of stored energy, like a bow and arrow. If you pull on it, there's stored energy there. If you let go of it, it's going to project that arrow. Or a rubber band. You can. A lot of people and a lot of kids want to shoot stuff with hornets. And then X is the distance, very much like Hooke's law. It's the distance that we've pulled this rubber band. When it comes to energy, we're going to use, the units are going to be joules. And the one thing I want to point out to you is energy was the thing for work, or joules was for work, and it's for anything that's associated with energy. So what I mean by this then is, as we said earlier, if you have energy, you have the ability to do work. If you're doing work, then you are using your energy. Right? And once again, the units for energy and work are joules. All right, I've got a couple practice problems here. A 2.5 kilogram rocket is shot off. It achieves a speed of 120 meters per second in 0.35 seconds. So, how much force did the rocket create? Well, force, as we know, is equal to m times a. I know the mass of the rocket. What I don't know is the acceleration. But I know that it started at 0 because it's a rocket. Its final velocity was 120 meters per second. And I know the time is 0.35 seconds. So I can find the acceleration by saying 120 minus 0 divided by 0.35. That turns out to be an acceleration that's equal to 300 and we're going to say 43 meters per second squared. what that does then is that allows me to go back up here and times it by my mass. So to find the force, I can say it is 2.5 kilograms times that 343, which gives me then 857 newtons. And I'm not going to worry about the decimal places. We can talk about that later. So that right there is my force. How high did it go in that 3.5 seconds? Well, that takes me back to my kinematic equation. YF equals YI plus VIT plus 1/2 AT squared. YI in this case is on the ground, so that goes to 0. It had no initial velocity, so that goes to 0. That leaves me then with just 1/2 AT squared. Well, YF equals 1/2 343 times this time squared. The time is 0.35 seconds. And sorry, I punched this in my calculator here. And we find out that the height is 21 meters. So the question then becomes, how much work was done in the first 0.35 seconds? Well, work, as we know from the other day, was force times distance. The force was the 857. The distance is 21 meters. So when we multiply those, the work turns out to be 18,000 joules. 18,000 joules, that's a lot of energy. Alright, that's work and it's energy. So there was 18,000 joules worth of energy that was used here to get it to that height. Calculate its kinetic energy at 0.35 seconds. Well, its kinetic energy, as we said, was 1/2 mv squared. So that's going to be 0.5 times the mass of 2.5 times this velocity of 120 squared. And and we get again 18,000 joules. So what that tells us then is all of that kinetic energy from number 4 is going to turn into potential energy. So how much higher will it go? Well, it's all of this 18,000 joules is going to go into potential energy. So if I say potential energy is mgh, and 18,000 becomes the potential energy. All it is now is plugging in the information we know, and we're going to get another height, which is that much on top of the original 21 meters. The mass is 2.5. Its gravity is 9.8. And we're solving for h. And we find out then that this rocket will go an additional 735 meters. That's not its total height. That is how much higher it's going to go after once the engine is burned out. So the engine got it to go the first 21 meters and got it going with, so that 21 and when the engine would stop burning, it had this certain amount of kinetic energy. And all of that kinetic energy now, as it keeps going up, is going to be transferred into potential energy because it's going to lose velocity and gain height. We find out that the height it gains is 735 more meters. So the total height of this rocket, the total height would be 756 meters. We're going to take a break here.